Okay, it's my pleasure to start off our final panel, and we're going to be discussing the future and many aspects of that. Charles Lawrence.
Thank you. And my glasses are still here. The first time I was in Italy was L'Aquila, CMB 25. I've been in Italy many times since, mostly for Planck, and I'm very glad to be here again, so thanks to the organizers. And Nicola was, I think, key in putting this program together, so it is wonderful to be here. My subject today is the future, and a restricted slice of it. I'll only talk about anisotropy measurements. We heard this morning about spectrum measurements. I'm a huge fan. They must be done. Tomo, after me, and Francesco this morning talked about LightBird, which aims to get to R of about 10 to the minus 3. I'll take for granted that there is a need to measure or put limits on R below 10 to the minus 3, say 10 to the minus 4. Also, to measure or put limits on the B-mode power spectrum for L less than about 30. As a practical matter, I do not believe either of those is possible from the ground, ever. Now, I want to emphasize that I'm using R just as a metric. And when I talk about the future and I talk about anisotropy measurements, I in no way mean to imply that R is the only thing that you get from them. That's not a discussion that I will say anything about. Just take it. There's a huge range of things that we're talking about, but I use R as a metric. It's convenient. My question for today, is there a path to achieve levels of equivalent to R 10 to the minus 4, and what goes with it? Considering possibilities, ESA, NASA, and the Chinese Space Agency are the only agencies that currently can do missions of the scale required. India, as I learned last night from Tarun, is coming along, and they'll join the club. But right now, those are the three. For CNSA, the CMB is not mentioned in the development program announced last October. It was a very broad summary, no details, but CMB wasn't mentioned. For ESA, Voyage 2050 has an L-class candidate for spectral distortions. Now, we heard all about spectral distortions this morning, but there isn't an anisotropy candidate for ESA in the Voyage 2050 program. But for NASA, there is a real possibility in the probe line of missions. The expected second NASA probe call in about 2031 offers what I see as the only credible opportunity in the foreseeable future, and I'm thinking many decades, for a mission that can do R around 10 to the minus 4 and everything that goes with it. Let me explain why. NASA astrophysics takes as its chief mission in life to implement as much as it can of the most recent decadal review. So what did Astro 2020 say about probes? Well, during the 2010s, there was a growing recognition. I'll keep up to date here. There was a growing recognition that the gap between Explorer missions with cost caps of, say, $350 million, up to $350 million, and flagships costing many billions provided a huge opportunity for science. So that was during the 2010s. To demonstrate this, to give Astro 2020 ammunition, NASA funded 11 competitively selected mission concept studies with a PI cost cap of $1 billion. And along the way, this became known as the probe class of missions. Astro 2020 took the bait in a sense, recognized a good thing when they saw it, and said, institution of a probe class line of missions with a cost cap of $1.5 billion per mission, a cadence of 1 per decade, and competed within selected priority areas identified by this and future decadal surveys, is a crucial addition to NASA's astrophysics portfolio. And they added the 2 priorities for the first probe class mission competition are a far infrared probe or an X-ray probe to complement the Athena mission. You might think that 1 billion and 1.5 billion are incompatible. The 1 billion is PI cost cap. The 1.5 billion is total cost to NASA, including the launch and the launch operations and reserves and all those things. 1 equals 1.5. Okay, that's Astro 2020 and probes. They made the recommendation, NASA implemented it. How about Astro 2020 and the CMB? One of the 11 mission concept studies was PICO, the probe of inflation and cosmic origins. That was input. It was never proposed. I remind everyone, it was never proposed. It was a report, a mission concept report, and it was input to 2020. Input also to 2020 was a well-advanced description of CMBS-4. CMBS-4 started in about 2015, and it came into Astro 2020 with the highest recommendation of the Particle Physics Project Prioritization Panel, P5, from the physics side. And this was the first time that DOE got into funding CMB. So, those were inputs. I'll come to what Astro 2020 recommended. You all know the most of the outcome, but maybe not some important details. But here's what Astro 2020 said, a couple of excerpts, about the CMB. Higher angular resolution and sensitivity CMB observations from the ground and in space will be needed given the difficulty of detecting the small B-mode signal amidst the polarized galactic foreground. Okay, strong support for B-modes and a statement, we need ground and space. Higher sensitivity and higher resolution CMB observations motivated to a significant extent by cosmology, section 2.2, will have a large impact on the understanding of galaxy formation as well. They certainly didn't take the CMB to be a one-number subject. The conclusion, put simply, was that CMBS-4, as detailed to start taking data in 2027, was ready to go, and PICO wasn't. So, Astro 2020 recommended CMBS-4 as its second highest priority for new projects on the ground, second after the much bigger ELT program, to be jointly funded as proposed by DOE and the NSF, and with observations to start nominally in 2027. But it also said, this is in section 7.5.3.5 of the Astro 2020 report. I will read it. As detailed in the report of the panel on cosmology, studies of the cosmic microwave background continue to provide data that address profound and fundamental questions about the universe on the largest scales and during its earliest moments. As noted by the EOS-2 panel report, space observations will unquestionably be needed for the best foreground separation and the lowest systematic errors on all angular scales, and especially on angular scales of greater than about 10 degrees. With investment in technologies this decade, combined with ground measurements, cosmic microwave background CMB probe mission could potentially be a compelling candidate for the future probe call in the 2030s, complementing the survey's ground-based CMB S4 recommendation. I'd like to emphasize that there was no other subject, no other kind of mission anywhere in the report that was mentioned for the 2030 probe call. CMB was very highly regarded scientifically, and the practical implementation was do CMB S4 now, study, work on foregrounds and systematics for space, and it could be a great thing to do in 2030s. Okay, so why wasn't PICO ready? Or, I'm not asking the question, I'm telling you why PICO wasn't ready. Two things, foregrounds. CMB S4 Concept Definition Task Force report in 2017 first showed that equivalent angular resolution was needed at low and high frequencies to deal with non-Gaussian structure in the synchrotron background. PICO had beam size strictly proportional to lambda, so big beams at low frequencies. And likely it could not deal with realistic non-Gaussian synchrotron foregrounds at the 10 to the minus 4 level. It's not saying it couldn't deal with them at the 10 to the minus 2 level or the 10 to the minus 1 level, but not at 10 to the minus 4. The second thing was about detector coupling. PICO used 3-color sinuous antenna lenslet pixels for the 21 to 462 gigahertz bands. The plane of polarization of sinuous antennas rotates with frequency, plus or minus 5 degrees over 2 octaves in frequency, to be quantitative about it. That's scary. It's never been demonstrated on a CMB experiment. That's scary, even scarier. Both of those problems were driven by the same thing, the 5.2 meter Falcon 9 rocket shroud, which limited the volume and design of the telescope, and in turn, the size of the focal plane. So what's changed? Well, considering Astro 2020, considerations, deliberations in 2018, 19, 20, 21, in May 2024, just over a year ago, the NSF said it would undertake no new experiments at the South Pole for at least a decade. As a result, CMB-S4 has spent the last year redesigning the experiment to be an all-Chile experiment, with first data now no earlier than 2035. Francois will talk more about this later on. The second thing that has changed, well, it's a big change. It's big rockets. Joe showed 2 of these before. On the left, Starship, with an 8-meter dynamic shroud. So it's 9 meters if you measure it with a ruler, but the dynamic shroud is 8 meters. And on the right, New Glenn, with a dynamic shroud of 7 meters. Let's compare that to the Falcon 9. Before we do that, here's the opportunity. Astro 2020 strongly affirmed the importance of CMB science. There's no question about that. And then concluded ground first, data in 2027, and space next, potentially a compelling candidate for the future probe call in the 2030s. The current probe missions now in step 2, the first ones in the first probe call, show launch in 2031. Add 10 years. So 2041 launch. But CMBS-4 is delayed by at least 8 years compared to when that recommendation was made. And we should definitely update, after 7 years, the previous probe study, PICO, focusing first on the following. It takes advantage of the big change, and that's the telescope. The design of the telescope, 3 mirror anastigmats have much bigger undistorted focal planes than PICO's open Dragoni design, meaning much more space. For detectors, no need for multichroic feeds with sinuous antennas. And the size, well, enough resolution, you can have a bigger telescope, enough resolution to deal with the non-Gaussian synchrotron foregrounds, the low frequencies, and the prospect to go to L greater than 5,000 at the higher frequencies. Do that at the same time. That's a different mission. Here's PICO in the 5.2 meter Falcon 9 shroud. Here's PICO. Sorry. It's kind of lost in filling up the 5.2 meter shroud and lost in the Starship. The Starship is just the outline of the 8 meter dynamic envelope. So you can fit not only PICO, but the whole Falcon 9 shroud with room to rattle around and add a few other experiments. There's a lot of room in there. It's a change. It's a big change. Okay, how large a telescope will fit in a Starship? I don't know. But to explore that, I started with the 5 meter, 3 meter mirror anastigmat design that Steve Payton made for CMBS-4 to use at the South Pole. That's the optical cross section from his paper that I referenced, which is a really good paper. The field of view of that telescope was 12 by 8 degrees at a wavelength of 3 millimeters. And it could accommodate 424,000, 136,000, or 63,000 F lambda pixels at 1, 2, and 3 millimeters. That's a lot of detectors. That's a lot of detectors. PICO only had 13,000 detectors, scrunched up in di and trichroic pixels. So the TMA focal plane in this design is just way bigger than necessary. All right, so in subsequent slides, I'll show you what that telescope design scaled to 3, 3.5, and 4 meters looks like in the rocket shroud. And I'll rotate the telescope so that the angle of the principal ray coming off is 69 degrees from the spin axis, as it was for PICO. Haven't calculated anything, haven't designed anything. I'm just putting pictures in pictures. So, 3.5 meters. Sorry, 3 meters. Looks pretty easy. Haven't tried to place it, haven't tried to make a spacecraft, haven't tried to do anything. There's a lot of room in there. 3.5 meters. Looks like you might have to work at it a bit. 4 meters. Maybe things are getting tight, but there's a lot of design flexibility in TMAs, and it has not been exercised here at all. This is the design that Steve made for a telescope to go at the South Pole. So, got to be studied. We have to figure out how large a telescope will fit. One thing for sure, and as far as design variations go, is with a smaller field of view, you make the third mirror, the one at the bottom, smaller. Okay, well, that's one thing. Move the whole thing down, more room. You get the point. Let me summarize. There's a credible programmatic path to a space mission that could get to our 10 to the minus 4. With angular resolution at low frequencies to deal with non-Gaussian synchrotron foregrounds, and angular resolution to deal very effectively with delensing, cluster science. I'm missing a slide here. Well, it's just words. I will say them. Angular resolution to deal with delensing, cluster science, other astrophysics, time domain observations, a huge range of things. I want to emphasize something that I think needs emphasizing after the discussion this morning. When I think about designing missions, when I think about designing scientific programs that involve experiments on the ground or missions in space, there are four things, four big considerations. The first one is science, always science, start with science. Then there's technology, and there's capability, which is broader than just technology. But finally, the fourth thing is opportunity. There's an opportunity here. There's a program that has been recommended by Astro 2020 and accepted by NASA to fly a probe every decade. We don't have to make that opportunity exist. We don't have to make it up. We don't have to convince anybody that there will be an opportunity there. Yes, it requires a proposal. Yes, there's a chance of not getting selected. Yes, there are all kinds of uncertainties. But there is an opportunity, and that's very different than saying, here's a great idea, here's a great concept for a science mission, and here's what it would take to do it, but with no clear path or no existing path at all of how you get to it. Convincing agencies to do things that they don't do, making up new things can of course be done, and it is done, but it's a much longer process than taking advantage of an opportunity. And so what I'm talking about here is there is an opportunity, and it's a credible opportunity, and we should take advantage of it. We should take advantage of the fact that rockets are much larger, and there's design space to investigate, to maximize a mission in a larger rocket. No guarantee, many uncertainties. We're going to start studying this in the fall, and I hope that many of you here today will be interested in helping with that investigation. Send me an email, a text message, carrier pigeon, talk to me today, whatever. Everybody will be welcome. I don't mean at the level where we pay you and you're working 24 hours a day on it. Not at that level, but at the level that we had a large group working on the PICO study, and it's typical for trying to put missions together. Okay, so the world has changed. There is an opportunity. We should take advantage of it. Thank you.
So as Erminia comes up, let me ask you, could this fit into the cost cap, do you think, of the program with a 4 meter?
I think that's one of the key questions that has to be studied. On the face of it, fitting a 3.5 meter telescope rather than a 1.5 meter telescope in a rocket sounds like it must be considerably more expensive. And it may turn out to be that. But the cost of rockets, remember what's happened with the cost of rockets. There are a lot of things happening in the commercial space world, including spacecraft buses and other things that are getting cheaper. So I don't know. It's a critical question, absolutely. And it won't be first on the list. Figuring out how big a telescope you can fit in there is probably going to be first, and how many detectors you want and can fit. But it's right after that. Yep.
Thanks again, Charles. So Erminia Calabrese will be our next speaker.
Well, while the slides, okay.
You can control the
Yeah,
advancement.
yes, it's working. Okay, so hi everyone. Thank you very much to the organizers for inviting me. I'm talking today on behalf of the Simons Observatory collaboration. And a lot of people from SO are in this room. A lot of the topics that we have discussed in these past days are active areas of work already for the Simons Observatory. Some of the things that I'll show later has already been shown, but hopefully this talk will pull everything together and give you a view of where we are, what we want to do, and what we are doing already. Okay, oh no, sorry. Let me say one more thing on this slide. So the picture on the slide that you were looking at, it's disappeared on screen. No, I wanted to go back. Yeah, that one. First slide, please. Yeah, that one. Yeah. Stay on here, please. So the image that you are seeing over there is a picture of the site. This is the Atacama Desert in Chile, before any bit of SO appeared, right? So this is showing what the plateau looked like with some existing experiments. Let's see if I can do this. This is the ACT telescope, for example. And in the next few slides, you'll see how this has evolved over the year and what we plan to have over there when the full observatory is up and running. Okay, so SO started as a project in 2016. The idea is to build and operate an array of 7 telescopes. 6 of them are 0.5 meter small aperture telescope, which I realized from Jamie's talk this morning for BICEP, that's a large aperture telescope. Well, for us, it's the smallest aperture telescope that we are working on. And then the other telescope is a 6 meter large aperture telescope. And you see here how the site is planned to evolve to accommodate the infrastructure that is needed to operate this. Together, when all of these telescopes are up and running, they will be hosting a little over 120,000 detectors, and these are all operating, both sets of telescopes will be operating in 6 frequency bands between 30 and 280 gigahertz. We had a number of years where we designed what we wanted to build, which type of telescopes we needed to achieve the science goals that we wanted to reach. People then went on and built, tested, and eventually deployed these telescopes to Chile, and operations have now started. So we are live, we are observing the sky. One additional recent thing that has been planned and we are very proud to do is to also make this a green observatory. I'll tell you a little more about this later, but the idea here is to reduce 70% of the power at the site with solar energy. And I think this is a huge thing for the community and something that we should all be very aware of these days. The collaboration has been assembled over the year. It started by bringing together the ACT and Simons Array collaborations that were already working at the site, and then expanded and grew to host now about 400 collaborators from all over the world. Okay, so now if we go back to the site, this is how things have evolved to accommodate what we initially thought we were going to build. So when we started talking about SO, we were talking about SO nominal. SO nominal was the large aperture telescope, not fully populated, so with only some of the optic tubes hosting detectors, and then a set of 3 small aperture telescopes. And this is what we presented to the world in 2019 with our science goal and forecast paper, saying we were going to build these telescopes to achieve our science. And then things evolved, and this is now what we plan to do. So I said it's a complement of 6 small aperture telescopes, the 3 nominal ones over here, 2 UK-built and deployed telescopes, one delivered by our Japanese colleagues, And then the additional expansion has been this Advanced SO project, which fully populates the Large Aperture Telescope. And this complement of solar power funded between the NSF and UKRI in the UK. Okay, so by 2028, this is the full assembly of telescopes and infrastructures that we will have to observe the sky. Now, what are we going to do with it? So obviously, a lot of our science goals fall within the remit of cosmology and particle physics. This was a next generation CMB experiment. We have heard about all the interesting things that we still have to do, and I'll touch upon a few specific examples later. But as we have learned with Planck and ACT and SPT as well and other experiments, when you get such sensitive images of the sky in the microwave, you don't do just cosmology, you open up a wide range of additional science that you can extract. For example, the astrophysics of sources and galaxy clusters, the physics of the Milky Way, and more recently looking into individual variable sources. And then, of course, while we do this, there is a lot of work to be done all the way from design, building, testing the experiment, constructing the pipeline, and then analyzing the data. And this means that there is this huge pool of talented people that are part of the observatory and makes things run on a daily basis, basically. Okay, so the 6 small aperture telescope are fully dedicated to B-mode searches, right? So this is similar to what we have seen with the BICEP telescopes. These are looking at deeply at a specific patch of the sky. We are going to cover 10% of the sky. And just to give a sense of the sensitivity we reach, we are projecting about 1 microkelvin arc minute when we have had 6 sats looking at the sky for 9 years. Now, what this means in terms of observations is that we map the B modes in the recombination bump and all the way down to the lensing scales. As Jamie said earlier, we are looking at a wider patch of the sky compared to BICEP, so we are less affected by delensing. And so in a way, this is a complementary way of looking at this signal and also a way to characterize it across the sky and check that there is isotropy of the signal in different regions. Now, if I take this observation and I project them into an R and S plane, we have seen many of them during the last few days. It looks like this. And now let me make a clarification here. I said some of these observations because this is the plot that we put out when we did the forecast for the nominal survey. So it's only accounting for 3 small aperture telescopes. We know now that we will have 6 of them, and so we will double the map speed to get to B modes. So this is the minimum that we forecast we can do. And the goal that we set was to reach a sensitivity on R on 0.002 or 0.003 according to the specific noise levels that you were considering for SO. And so this is going to be our way of searching for primordial gravitational waves, testing inflation models, ruling them out or favoring them, or trying to characterize more broadly primordial perturbations, looking even at scenarios that don't account for inflation at all, but you can just characterize the spectrum of your perturbations and study their origins. The Large Aperture Telescope will do everything else, right? So the sets are dedicated to the science goal of going after inflation and primordial gravitational waves. The LAT has the job of mapping out all of the scales that are remaining to be measured that Planck and ACT and SPT haven't done or haven't done to high enough sensitivity, and we can still push down the sensitivity on those scales. So here now we are mapping out all of the temperature anisotropies and the E modes and the lensing signal of the B modes. And these are the regions where we do all of our cosmological model tests, right? This is where we improve sensitivity on parameters from lambda CDM or on all the extended models that we want to test, because usually the signatures of those models can be distinguished at small scales. In this case, for the LAT, we are aiming to look at as much sky as possible from Chile. So the minimum target that we have is 40% of the sky, but we can reach up to 70, and we haven't yet decided where in that band we will sit. And here we have a resolution of 1.4 arc-minute, or our data reached the resolution, and about 6 microkelvin arc-minute combined sensitivity and 9150. Again, with the nominal SO, it will be better now that we know that the LAT will be fully populated. So we had an update on our science goal and forecast paper presenting the increased capability of the LAT. And this plot here is actually showing what the full LAT can do. But the projections that you see in the next slides are going to refer to what we said initially. So when I say you can do everything else, I mentioned the parameters of lambda CDM. I haven't made an explicit mention here, but we are projecting a 0.5% measurement of the Hubble constant. So this will be another data point coming from the CMB to be able to tell something new or maybe not in the current discussion that is happening about the Hubble constant. This is an example. I mean, Massimiliano already showed this plot from the recent ACT data. This was the version that was in the SO paper. But then again, it's showing how you can set limits on relativistic species or on the nature of dark matter by measuring its property here. It's a specific dark matter proton scattering, elastic scattering constraints. The other thing that the LAT can do is to enable a huge range of science that falls into the bracket of cross correlations. Our survey by design is meant to overlap with many other experiments. We have the full DESI footprint. We will have full overlap with Rubin, large overlap with Euclid. And there is a lot of physics that you can extract by bringing together different epochs of the universe. And in particular, anything that depends or affects the growth of structures will be characterized at high sensitivity with this. I mentioned earlier opening up new avenues also in galactic science. We have already seen it with the Planck observations. The galaxy is there, you get it, you want it or not. But you now have very precise measurements in both temperature and polarization of the galaxy, and that will help you learn about the physics properties of the Milky Way. Transients and variable sources is something that our community has only started to pick up. We have examples now from both ACT and SPT that these appear in our data. We can see them, we can track them. And this is something that we are now building larger capabilities for, to be able to work in tandem with other observatories to follow these sources and then try to interpret them. There was a question yesterday, I don't remember from who, about Starlink impact and what's being done in SO. I just wanted to say that a part of our transient pipeline that is being developed is specifically going to look at how to detect those satellites and then potentially remove them. But we are not predicting to be heavily impacted by them. Also because all our science goals rely very little on observations at low frequencies. Okay, and then, as I said, it's happening. We have had first light for both SAT and LAT. Now I'm going to show you a few images that tell you that things are progressing. So this is an image of Jupiter for the first observations of the SAT. That was our way to measure the beam and the beam shape and make sure that everything was working well. And then you already saw these preliminary maps in Nicoletta's talk, but basically this is just showing that we now have two middle frequency 9150 sats looking at the sky, and we start having Q and U maps that are starting to show the polarization pattern just as expected in the region that we are targeting. And then you can look more specifically at 90 gigahertz only from one of the two telescopes. Lyman showed you the polarization version of this, and this is the full complement of temperature and Q and U stokes of polarization. And one more map comparing ESO and Planck on galactic scales here, just to show that, again, with ESO, we are recovering really well the large scales and demonstrating that the instruments are performing really well. The LAT joined the party only recently. First LAT was in February this year, basically. So I don't have any map to show you yet, but this is the first step, and this is an image of Mars showing the beam that the telescope is up and running. And I'm concluding just with a comment when it comes up. Well, we are part of the Future Perspective session, and ESO is going to be with us for many years in the future. But I just wanted to highlight that we are crossing the line. This is really talking about the present. This is happening now, and it's great to be able to lead this transition into the future. Okay, thank you.
Thanks, Amir. We'll come back to questions later. Francois Boucher is next. Unfortunately, John Karlstrom had to cancel at the last moment, and Francois has kindly offered to take on part of his discussion.
Yes, so last week, John told me that he had a family urgency that, and he really regretted not to be with us because so many friends and so on. So it's really a shame he cannot be with us. But then he called me up, say, Francois, can you help? That would be nice if I was not completely absent. So I said, of course, John. So I'm given 10 minutes to cover some aspect of SPT, SPO, and S4. Not quite as John would have done, of course. I'm not John. But anyway, so let's proceed. Should I operate this myself, or?
It's best.
Yes. So quick reminder, just like we had SO, well, there is a South Pole Telescope. You all know pretty much all of this. 10-meter class, 3 frequencies, full width of max as given by the size of the telescope. We are now currently at the 3rd generation of focal plane, and this was the 3rd generation was deployed in early 2017 with about 16,000 TES operating at 300 milli-K, and all of this is pretty well known. Now, later developments, and I will come back to this, have been largely increasing the fraction of the sky that will be surveyed. And okay, so it's a smaller collaboration as compared to SO. I mean, in the beauty context, who is the smallest? We're probably one of those, not quite as bicep keck, so all right. So there are essentially 3 surveys to talk about. The one that you all heard about, I don't know whether this works. Well, all right, you know the bicep field, that is a little dotted part. So everything so far has been the 3G main field, which is the 1500 degrees square, which is in blue, and all of the data was taken, apart from adding a little bit more till next year, and you can sort of see the noise level that will be achieved. But then we realized that given we could also do a much larger fraction of the sky, but not quite as deep, but still covering, essentially a quarter of the sky. And so we proceeded, and that's done. That's in the can. So it's not future data. It's been observed. I didn't say that it's being reduced. I mean, it's being reduced. I mean, we have several people, including in my institute, making maps. So it's happening. But as you know, this is a very long way from there to cosmology. Anyway, so first, and recent and upcoming, it's about the main results. There are a few things. One that is well known already, which is the lensing map, and this one has the originality that this is only on lensing, only on polarization data. So there is no temperature there. It's only SPT, and that's actually using a novel method, which is going away already from quadratic estimators. And so that's the result. And what you can find in this paper by Jay and Marius, that the E-mode spectrum at L greater than 2000 and the lensing spectrum at L greater than 330 are the most precise to date. So it's there. I mean, it's not future, it's what you can get your hands on. So there were a number of constraints, and the thing that you can sort of see from there, I don't know whether this works, I don't know how this works, but, yes. So this is SPT for this without temperature, right? I mean, this is purely polarization. You can sort of see the usual thing. The beauty of it is SPT and ACT, I mean, confirm quasi-independently the low H value that within lambda CDM was first announced by Planck. Okay, that's, and this is completely consistent, as you can see. The other thing that I want to show is something a little bit less common, is to show the contour when you are using Planck, but only the polarization from Planck, SPT, and ACT. So these are the constraints from polarization only. And as you guessed it, the little blue thing is SPT. All right, so SPT only polarization is already there. These are the constraints you get today. So sorry, it's not in the future yet. So now there was even more recently a joint collaboration paper. Yes, this thing happened between ACT and SPT, which is a unified and constant structure growth measurement. And here is a result, which is even, as you can see, we're getting close to now. This is 2504 on archive. Again, H0 66.4. So this is essentially the grand unified lensing spectrum that we have today. That's the situation as of a few days ago. Now we jump into the future. So this is really imminent. It's, I feel ashamed to be here while this is happening right now. So these two guys are leading this. This is an extract of what will be the draft of the paper, which is in the final review by the collaboration. Of course, I'm not giving you the central values, but you can judge by the error bars what will be there. Okay, I mean, that might change by a small amount, but these are preliminary numbers. Due to the fact of our scanning strategy, I mean, we don't have as much power in TT that, like a full complement. So you can see that the NS error bar is unfortunately a little bit large. I mean, it's larger than ACT. But the interesting thing, I will not tell you what is happening, but the interesting thing is we'll see if it goes in the same direction as ACT at going at larger NS as compared to Planck or too lower NS. So keep posting to get the answer. I guess there will be at least one reader of this. Okay, so projections. Now we have in the can, as I was just saying, the complement, which are there, that is both the summer fields there, and then and those maps are existing, all right? They are going through all the null tests and all of that. And we're starting to do the maps in the green area, which is the extension, the wide survey, which is 6,000. So in total, this is a quarter of the sky. So the expected signal to noise, it's written out. This is in Prabhu et al. This is standard practice of, essentially Fisher matrix analysis. But you can, so of course in TT, I mean, it goes better than Planck, only at a scale which is about 2000. All right, so Planck remains unchallenged all the way to 2000, and then it's, the extension takes off. And then for essentially all of the others, like you look at EE and Phi, this is a much larger signal-to-noise rendition than Planck. And so very soon, I mean, we would have completely superseded Planck in some regimes. All right. Now, future constraint. Well, what we think, I mean, if everything goes according to plan, which we all know, I mean, it's a difficult proposition to transform Fisher matrix predictions in terms of, or assessment into reality. But that's essentially, with the data we have in the can, we can have an improvement of the figure of merit by the 130. Okay, so that's pretty substantial. So it's comparable to what is expected for the first future 2 years of ASO baseline, which of course we know that there is also the extended part. So you can sort of see the current view of the timeline. So somewhere here we should, if the analysis proceeds well, we'll fill the gap all the way till SO gets its analysis out. So as an example of what we'll be doing, essentially a number of the extension as compared to lambda CDM will be improved by at least a factor of 2, each of them. Well, you can sort of, this would be in units of Planck, everything. So if you see this is twice better constrained than Planck. You can do this also for 2-parameter extension. I mean, all of this is sort of standard things for proposal writing. But the important thing is the data is in the can, and we are working to make it happen. Now, South Pole Observatory, as you know, this is, there is not only SPT, but we have BICEP and BICEP array and so on, and that was, and Jamie told us about the developments, and these were the standard forecasts. I think I'm missing something. Oh yes, well, it's not showing everything I wanted, but okay. So that was expected plan with a sigma of 10⁻², sometimes around 2009. 29, it's here, right? Now, well, all right, you cannot see this, but SPT3G plus, there has been not a reformation, but an optimization of the proposal that had been funded to actually replace it with a more powerful focal plane, which will have 7 times mapping speed of SPT3G, and all combined data will lead to a 0.5 micro-K arc min. 0.5 micro-K arc min, if you hear me. It's not a typo. And if everything goes according to the plan, if you just translate this in sigma r, we're talking sigma r of 10⁻3. I'm not claiming this will be what we will delivering, but in terms of sensitivity, that's to be what we'll be reaching. So the important, so now what you see here is this is assuming that SPT3G plus will be starting operation, that is being on the sky, in 2029. So in some sense, this is a complement of the previous slide. And with crossing the 10⁻³ around 2032. Again, getting the data, which is, of course, the analysis out is a maybe different proposal. Okay, but the important point is our forecasts are anchored in the demonstrated performance of BICEP and SPT. I mean, it's the thing that we know we can do because it's largely data in the can for quite the early part of this curve. CMBS4, okay, well, I'll be very short. I think most of us know about the sort of somewhat sorry situation. Initially, I mean, we had the idea of an ultra-deep sky survey, 3%, mostly from the pole, and a deep wide covering 60% of the sky. All right, and then we have countless documents that you all know, and we've gave all the details about what science we could do and so on. I mean, so I won't do anything of this to the benefit of not being totally exhausted, all of us, and being able to go for dinner. But ta-da, May 2024, NSF declined, as was already said by Jamie, to enter CMBS4 into the major facilities design stage. They had other needs at the pole. But on the other hand, I mean, they will continue supporting the existing infrastructure and as well as the planned operations. So we can be hopeful that the plan that I showed you will be not dodged by the MAGA country, whatever. So for S4, the project has worked into a revised concept as requested by the agencies. So there were a first report about what could be done, Chile only, new infrastructure, then what would be the status of the other experiment that was led by Charles. And then the third thing has been trying to find a way of using the existing infrastructure to essentially get to the similar objective with a reduced cost. The plan has been submitted to the agencies, I forgot, like a week ago or two, maybe a couple of weeks ago. We will hear about it in a few months. So it went well, Jim Straight said, but that's all I know. All right, so it's all about, I mean, I'm sorry, but I don't think it's worth spending any more time. I mean, that all depends on what is the agency's response. But we have, the concept that has emerged is to go through two phases, and having a first phase, which is, implement as quickly as possible, get something going for S4. And then what is phase two is largely open yet to discussion. And there was some element of that were given already by Jamie. All right, now my talk. All right, so now I dropped John's view. I must say I'm a little bit embarrassed to talk about this audience for several reasons. One of them being that I had to freeze everything Sunday before going, and so without the benefit of all the interactions. So now if I could change things, say by yesterday night, I would have given a totally different talk. So I will try to still say what I want on slides which have nothing to do with it. So it's an interesting exercise. Anyway, to me it's pretty simple. I mean, this is a long-term scientific perspective. It gave me a license to dream. To me, it means essentially extract all of the information that the CMB contains. Okay, so essentially, let's go to cosmic variance. And as in Planck parlance, it would be to be only limited by our ability of removing foregrounds. But otherwise, it shouldn't be a limitation by sensitivity. All right, so that, of course, this is only part of the story. The CMB is also about a spectrum, and there are the spectral distortion science, all the way to recombination lines, as was mentioned several times, as well as the non-Gaussianity that you can probe by cross-correlation between mu and t that we all know about. But there are a lot of challenges along the way. So one thing that worth reminding, which we all know for a very long time, that is information scaling. Information is scaling like L max to the power 2.5. So yes, we want to go to cosmic variance all the way we can to extract as much information as we can. We want to do high order statistics. I mean, lots of the extension on the particle physics and fundamental theory call for some type of non-Gaussianity, or intermittent maybe, possibly, but not only. All kinds of other things. I don't want to spend too much time on this, but I resurrected a slide that we had prepared with Eleonora for the PRISM proposal, which was to sort of say, well, what is the increase in the figure of merit, which is essentially inverse of the volume of the allowed parameter space after the experiment is made, going all the way from COBE, pre-WMAP, WMAP, Planck, and then, well, essentially this was PRISM. Now, the interesting thing is, of course, the more you open the parameter space, the more you gain by having this sensitivity available. What you can sort of see is that, there is a very large factor of compression of the allowed parameter space that is still available to us. I mean, we shouldn't forget this. So, of course, the illustration here is saying lambda CDM, well, that's actually minor, but as soon as you throw to it W, sum of neutrino masses, and F, well, you heard about all of this during the week, so I'm not going to repeat this. But there might be more. The point is, we want this reduction in the allowed parameter space, and it may very well be that none of this is sufficient, and it's probably the hope that somebody like me has, is that we'll be surprised along the way. So let's get the means to be surprised. Yeah, all right. One thing that's really close to my heart is actually reconstruction. This is the reconstruction of the power spectrum from the early days. This is COBE, pre-WMAP, WMAP, and Planck, finally getting to the point of NS different from 1 at 8 sigma. And of course, we want to look at all kinds of possible signatures there, oscillations, whatever, you name it. Let's see. Yes. I think we all know about this. This is Dreamland. It's great, but we have to overcome quite a number of side difficulties. Sensitivity is one. This is about what the instrumentalists do, but there is the other big leg, which is systematics, and we all know that this is actually the rule of the game, plus foregrounds. I tend to also emphasize, given my own background, that, well, even if you have great data, that doesn't turn into great science. You still have a lot to do. You're only half of the way through, I would say, and we have to extract the most from this expensive data flow. And it's improved theoretical framework, of course, but it's also improvements on the data analysis. I remember very well when we were writing the proposal for Planck, there was no way we could perform the analysis with the existing computers. I remember that doing this at the resolution we were hoping, it was 1 million hours of CPU. And it turned out this was just minutes by the time we were doing this. But we had found other ways of spending a lot of computer power, and of course it's just, the curse is that on one hand we have people that we need to have very detailed simulations of everything that is on the technical side, you know, how we describe the instrument, how are we capable of reproducing the null test given the way we analyze the data. I'm really talking, describing the residuals of the null test given our understanding of the hardware. And in Planck, we ended up, after a lot of effort for the legacy, about 100 simulations full end-to-end. Just a ridiculous number. On the other end, of course, we all wanted, from the theory side, millions of them, but then the trade-off is you do millions of them which are of low fidelity. So I think there is, I believe that the future here is about emulators that are essentially, you learn from detailed simulations to be able to do a lot many. But okay, these are just issues we'll have on the path, and something that might be of interest for immediate future, that is S4, say let's analyze together SO and SPO data. Well, none has been engineered yet to do this, to my knowledge. These are different pipelines, different people, using different way of even making maps. Okay, it's not on the same format. So just making sure that we can work together, I think will require substantial help from the agencies, if I may say so. It's not only about new hardware, but I think that there is a tendency that we all had to underestimate the cost of the analysis. And I will let it at that for this point. Now, all right, you know, yes, that's fine. So I will skip this. I mean, that's obvious. I just want to sort of also remind, I mean, or stress what Charles would just say. Well, you know, a TMA is like SphereX, but we just want to do SphereX not 20 centimeters, but sort of 5 meter-ish. That opens a gigantic focal plane. And so Charles liked to think more about having low-frequency foregrounds at high angular resolution. I'm more turned on by having the sky at high angular resolution, doing delensing over the full sky. I think this is just a fantastic future if we can make it real.
I want it all, and so do you.
Yes. Well, because I actually pinged you. I mean, you remember I was skeptical in our initial conversations. Anyway, but let's not forget, I mean, particularly, I don't know if Rashid is still, yes, Rashid is still there. We know that there are all kinds of physical mechanism imprinting, spectral distortions, which each of them is a chance at getting a new phenomena of interest. And we had Nabila explaining to the next step and so on. But as of now, the reality, it's another treasure trove which is still mostly untouched. So, you heard about what a pixie light could do. This is essentially filling the gap in terms of between what LISA, the SKA, and the CMB is currently doing, so that's exciting. Again, this is a very tall order because, as Joe has eloquently said, I mean, what we really want is not getting at this pixie sensitivity but the long-term goal is actually to get the recombination lines. And we'll have all fantastic science, but to me, I'm sick and tired to write proposals about all the great science we could do if we had the means to do it. I mean, I've gone through so many times. So I think the real question is how we get the money, or at least how we get the go-ahead to actually go and build it. That's the only real, because I'm too old, and so now I'm growing really impatient because I'll be 70 in just a few weeks. So I can't wait till 2000, whatever, 55. So I know, Joe, you are generous, and you say, well, let's plant trees for the others. But sorry, I'm not that generous. So I really think that our work is actually, our collective work should be to sort of get together and try to come up with a plan that is sort of acceptable by essentially everyone. This can happen. I was tasked twice by the French community to write a roadmap for the French science. And despite all the different inputs initially, we converged to a roadmap that was essentially accepted by everybody. Unfortunately, the recommendation that was number one was kicked out by ESA. All right, so you can write roadmaps, but all right. So again, it's not only getting a roadmap, it's to also get it swallowed. So predicting the future is hard, predicting is hard, especially the future, but I'm sure that the CMB will remain a cornerstone of cosmological research. I mean, that's just not, I mean, it's obvious, but the question is how we get it to be for real. And so I'm confident that we'll keep, pulling this tree of, here are theories and here are data analysis techniques, I mean, that I got from the paper by Di Valentino et al. Yes, it's there. So let's try to see how we can make this great future real. And I think I will stop here. And
Just hold that. Tomo, it will come up.
It's just aimed at a speaker. It's highly directional.
The next speaker's coming.
Yes, Tomo.
That you mentioned that Francois was able to put to side the subject
Need a new chair.
All right, thank you very much. My name is Tomotake Matsumura. This is the last talk, last talk, so it's been great days and it's been an honor to be invited, and thank you very much to the organizer. And we went through a lot, and probably all the things that I'm planning to talk has been already talked. And so that's my dilemma here standing today. And I was going to say that this slide has been submitted on Sunday, and so I didn't have a chance to revise it, but that excuse has been already used by Francois as well. So it's really, I have to squeeze myself. But just to remind myself why I'm standing here, it's because this was 16th anniversary, so that's congratulations. So I would like to talk Lightbird in the context, which is basically starting with Penzias and Wilson, and a lot of great experiments that we have gone through, together with, I used a picture for space mission just because Lightbird is a space mission, but that doesn't mean that all its many ground and balloon telescopes also play vital roles. And in this context, a Lightbird comes in here. So this is already a space agency selected mission, and we have a plan. So in that context, this is all the institutions that participate into Lightbird. And Lightbird has a joint study group consisting of roughly 400 researchers from Japan, North America, and Europe. And this is a recent pictures that's been taken from the face-to-face. Lightbird has been spoken by Francesco and other people with also scientific content. So I'm going to review that, but also since this is my luxury of speaking at the last of the session, so I'll try to sort of summarize and remind. So the goal is to definitive search of the BMO signal from the cosmic inflation in the CMB polarization and making a discovery or ruling out the well-motivated inflation model insight to the quantum nature of gravity. And inflationally or primordial beam mode power proportional to tensor scale ratio, as we've been all talking about, and the current best slip is that. And so the power spectrum that's been shown there is all this, the measurement that's been already made together with the projected LightBird data points. Now, the goal is to search at the sensitivity of 10 to the minus 3. And also the value of space mission is to be able to cover all the way to the large angular scale. And that means that space mission has a luxury to cover a reionization bump and recombination bump. So this is a very important feature that we're trying to achieve. Now, what does that do? So this is also a topic that's been covered a lot. So huge discovery impact evidence for inflation, knowledge of its energy scale, and distance travel by the inflaton. So the right-hand side is in the case that R is finite value if the nature is kind, and the right-hand side, the bottom, is in case of R is 0. So the detection of R beam modes by LightBird with if the R is 10 to the minus 2 or above would imply the excursion of inflation fields that exceed the Planck mass. Such a discussion would constrain theory of quantum gravity, such as superstring theories. The upper limit from LightBird would disfavor the simplest inflation models. And so this includes monomial models, alpha attractor with a super Planckian characteristic scale, including Starowinsky model, and models that involve Higgs field as an inflation. So this is really the signal that we're going after. Now, also this challenge has been highlighted so many times in various talks. Yes, there are challenges. The beam mode signal is very faint, as we know. And so LightBird is targeting sensitivity level in polarization roughly 30 times more sensitive as compared to Planck. And this extremely good statistical uncertainty must be going parallel with these three items, instrumental systematics as highlighted by Francois and many other people already, and the galactic foreground and lensing BMO signal induced by gravitational lensing. So to do that, how can we overcome? And this is the current, the nutshell of LightBird. So JAXA L-class mission was selected. So LightBird's selected mission, as I mentioned already, in May 2019 to be launched by JAXA H2 rocket. And this is a 3-year survey from L2, large angular coverage for the sake of foreground removal, covering something like 40 gigahertz to 400 gigahertz with a 15 bands or so, and degree scale, angular resolution for precision measurement of CMB BMOs. And the final combined sensitivity is something like 2 microkeV per minute. So that is the nutshell. When it comes to detail, as Francesco was mentioning, was it yesterday or today? Sorry, today. Thank you. I'm so overwhelmed with the flood of information, which I fully enjoyed. After ICE's JAXA mission definition review last year, LightBird is under a rescope study to consolidate the mission feasibility with the same scientific objective. And so, and the LightBird collaboration will spend approximately 1 year from that point. And so we're trying to have to show this the study of the information plan this late summer. So this is the status that we are here. So mission is selected, but at the same time, this reformation study and all the detail came from Francesco. So I'm not going to repeat. But this is actually came out to be an opportunity to revisit our mission. I think a lot of things have been said today about the future prospect, and this is the future session. So this LightBird is definitely fall into the future, but at the same time, this is an ongoing future which is a bit funny statement, but this is really what's happening. So one side, as a scientist, there are so many things that we want to achieve. There's a wish list, dreams, and a lot of things that we want to achieve, but at the same time, that has to be realized as a real mission. So this, the collision, the good collision is actually happening. And so that is really the time that we're spending for a year right now. But then the Lightbird, so far I have been only talking about the tensor to scale ratio, which is a big driver, and that is the only driver in terms of the mission design. But I want to make sure that we have to remember, once a mission like this be launched, we'll have a full sky map, and they provide rich science outcome as we have witnessed COVI, WMAP, and Planck. If you go to the archive or any other the paper that you can find on the website, it's depressingly so many papers that you can find and so many sciences that are coming out. And that is the notion that I want to make sure that you bring back with the space mission. And so, for example, this is a bit worthy slide, but mission specifications are driven by the required sensitivity and OR, as I mentioned, but meeting those sensitivity requirements would allow to address other important science outcomes. For example, characterizing B-mode power spectrum, search for source fields, so we can really do a shape characterization, for example, in a B-mode. And also, you can also look at E-mode. This has been also another big emphasis. Large-scale E-mode. In a way, I don't mean to be cynical, but thanks to Planck effort, and also thanks to Planck team leaving a little bit of homework to be done for the future generation. And so E-mode, low L, is to be, there are some room to be improved by factor of 3 or so to the cosmic variance limited. And so that is one thing that we can definitely do from space. Reionization. And that leads to a neutrino mass. Again, this has been discussed extensively. And also constraint on the cosmic variance, birefringence, which was covered by Eiichiro, also pointed out by many people. And also SDFX, thermal diffuse relativistic correction, constraint of the primary magnetic fields, elucidating anomalies. Anomaly has been pointed out a number of times. Once we get this full sky map, polarization with this depth, there are a lot of things that we can do. And galactic science, characterizing SED, large-scale galactic magnetic field, models for dust polarization, polarized compact or point sources, and also that could increase the, despite the fact that Lightbird is lower angular resolution as compared to the telescope like ACT and SPT. But Lightbird will be observing full sky for 3 years. So any time variable sources that we may see with appropriate signal level and a time scale, we should be able to see that. So all this study is ongoing, and these are the science outcomes that will come in a way by free together with a tensor to scale ratio. So this has been also highlighted before, but just to emphasize that this is a word that came out from Lyman about the value of the reionization signal from E-mode that is granted. So Lightbird will provide probe a cosmic variance limited measurement of the E-mode power spectrum at a large angular scale, and this will lead to a reionization signal to the cosmic variance limited level, and also this leads to a neutrino mass, a factor 2 improvement on sigma on the total mass of neutrino. And this is a very good example of the entrance point to the synergies with the other probes, obviously on the ground, and as well as the other probes, galaxy clusters, and so on and so forth. Okay, so to put this back in the context, so I started my talk in this, and final word here, 25, and I took recently a PI-ship after a great effort done by Musashi, a founding PI, brought this project all the way to here. Now, to put even this context, is this the end of cosmology? Obviously, no. There is still some room, the white area on the right-hand side, and this is very short description, which I can talk about it, but also we have a dedicated session. Definitely, there are a lot of synergies that we can look for with the CMB telescope on the ground in 2020s and 30s and more. And even after LightBird, what's going to happen? This is a very important notion that we share. And so that we talk about the science, but also technologies, and also people. Now we're talking about 2030s and 40s and 50s even. And so someone has to lead. Who's going to lead that? The community has to have this, to pass on this, the momentum toward the next generations. So I think in that sense, LightBird can be useful for science-wise or technology-wise, or even as a stepstone for the next generation. So I want to make sure that LightBird is seen in the context and play a role in this community. So I think always the last slide takes time to coming up. I don't know why. Oh, there it is. So LightBird is a JAXA mission for precision measurement for CMB BMOS under the international collaboration with Europe, Canada, and the US. It is the only space CMB mission planned in the 2030s currently. It is currently under reformation until 2025 fall to strengthen the mission in the procurement plan and its feasibility while maintaining the science objective. The natural consequence of the high precision millimeter wave, all sky polarization map, there's a rich science outcomes on top of CMB BMOD itself. And we want to make a LightBird a meaningful step in this observational cosmologies that you all contributed to bring to date. And this includes enrich the synergy with the next generation ground-based CMB telescope and other initiatives. And this international teams in LightBird is actively conducting reformation investigations so that not to lose this opportunity. We do have opportunity. We grab the opportunities in our hand. This is not something that we're looking for. Rather, we're trying to keep that, and so that we will play a scientific role in this community. So thank you very much.
Okay, so Tama, please join the panel. So now we're going to open up for discussion. Let's try to keep this optimistic. We have a glorious future ahead of us in the CMB. Questions for the panel members? All right.
Yeah, so this very ambitious PICO design, and that's great, right? On the other hand, Lyman said that we should only do the things that can only be done from space. But I think there's a lot of overlap between what PICO would do and what it can be done from the ground. I may be mistaken, so I just want to know your thoughts on this point. Of course, I have nothing against doing everything from space, right? Yeah. But I just, in the light of what Lyman commented, I just wanted to see your thoughts.
So first of all, Lyman is not God. Okay, so one may dissent about his opinion. I think we should do, he did add, because he's a careful guy, that there were also timing and financial considerations. So this is also where you do things best, and in the, so that needs to be included. I think I really want to see the full sky, not only, you know, a fraction of the sky. I really want to be able to tame foregrounds as well as it's possible. So I want a frequency coverage. So we have all kinds of reasons that ground is not enough in the current plans. So I think there is a pretty compelling reason to go to space. And the question is, why are we losing all this time we should already be way advanced in preparation to sort of take the following step to things that we've been showing. I mean, collectively, I'm not saying me in particular. We have the 10-3 range in view. We should be preparing actively for what will be the next step. That's my view. And we have all kinds of obvious reasons to go to space. I gave only 2, but it's and Lyman gave a few more: thermal stability, I mean, all of that.
Actually, I'm not going to disagree with anything, but I want to, so Jan Tauber, I don't know if Jan is still here.
He's here.
Good. He came up and he said, you know, I wasn't strong enough and I was too subtle in my praise of Lightbird. So I want to make sure, so you should not take that away. I think it's a great mission. It is, I think as Tomo just said, there's a real opportunity here. It will advance the field. We don't know what's going to happen in the future. That mission, maybe we go to a spectral mission in the future, then Lightbird results will be around for 100 years. And that's an enormous opportunity. And I think we should rally behind that, as well as everything else, but that is almost a bird in the hand. And it'll be great.
But my impression is if we are to rally behind Lightbird, Japan will need some aid from other countries. What is your view on that?
I'm the wrong guy to ask for that.
Okay. Anyone?
I think you should say something.
Well, a couple of things. Lightbird's going through a change in design that will have a considerable impact on what needs to be built. And yes, they don't have everything lined up now, but my understanding is that they're on a path to get there. And so yes, they need things, and not everybody has signed on the dotted line, but I'm optimistic. Now, why should I be optimistic? We should see if Tomo is optimistic about that. But I just want to reinforce that doing Lightbird in space as fast as it can be done is a globally good thing. And Eiichiro, to come back to your original question, Francois listed some of the things that cannot be done from the ground ever. And I'll just mention the 10 gigahertz to a terahertz frequency coverage is simply impossible from the ground. And the all sky, you could figure out a contorted way to get all sky from the ground with experiments in multiple locations, and it would be pretty contorted. But I'd like to suggest that one consideration that we should make is what's the most effective way to get the science? What's the optimum way to get the science? And we should think that first before we think about all of the political science aspects. So one important factor is that the cost of the ground experiments has increased enormously, and they're absolutely approaching a limit. And I think pretty much no amount of money will get very much beyond the things that are thought up now. But you can get beyond that in space for sure. So think of it as the next step. Remember the rule of thumb, 1 detector in space worth 100 on the ground. So Julian will point out in this end of Moore's Law era that the advantage of having fewer detectors counting for more in space is huge in terms of data analysis. There are many considerations like that. What I want to see, I'm a big fan of CMBS4. I'm a big fan of SO and SPO working on the ground now, taking data. I'm a big fan of Lightbird. I want to see them all done. That combination of those missions all together would be fantastic. Let's do it. And if I could just repeat, the single point that I made is for a big mission in space, there is a path that we don't have to invent. Let's take advantage of it. let's get together and work on that and do it.
I'd like to be blunt for a minute. I mean, we have a problem with Lightbird. This is new. I knew it's breaking news. I mean, Lightbird has a problem of detectors. There is a technology that is available at JPL. The money is missing. Okay, I mean, that's very simple. Lightbird misses 70 to 100 million to actually be done. So can we sort of all agree that, this is a priority for our field to make this happen? And we need the US. I mean, even though this is a Japanese-led experiment, for the time being, sorry, I mean, I'm not the PI, so I can be free to say all kinds of freaky things. The reality is we don't have detectors yet. And we have a vague plans from development in Europe, which I don't know whether this can jibe with the time scale of JAXA. So the reality is, can we all recognize that this is a fantastic opportunity, as Lyman said? Can we maybe even sign a letter to NASA, sort of explaining, well, maybe you could help a little bit with ESA? I mean, maybe addressed to both of them. Just think of this. I mean, the opportunity needs to be materialized, okay? And for now, we are in great danger. I mean, or they are in great danger, but I think CMB field, okay, to let this opportunity go. So we should stop, all these sort of strategic consideration for the 2050s. They have a key point very, very soon, and the agency will decide, well, do we pull the plug or not? I mean, that's a reality and many of you know about this, but I thought that I will be the blunt guy that is sort of talking about the elephant in the room. All right, so I say so.
Well, we need to hear from Tomo.
Let's see, Joe.
Of course, I mean, but I can say things that you cannot.
So look, with Lightbird, I'd just like to go back to what I was arguing beforehand, which is try and maximize the probability of getting it off the ground. Simplify it to the bare bones, to the, make it as simple as possible for the science schools and
Agreed.
Don't go beyond it. Okay, and make it as simple as clean as possible. And let's see what happens. But
Agreed.
park the more difficult stuff.
Agreed. Maybe
You still
Tomo,
need detectors, of course.
Tomo, you should grab the mic.
It's getting a little late, so I just wanted to ask Francois, why are you so hungry?
Because that's my nature. I've always been. Sorry.
Although we need to lighten up the spirit a bit. Although Lyman's not God, I wanted to re-emphasize his point. He just said some time ago, what is it? Planck, WMAP data, COBE, of course, prehistoric, ACT are public, everything else is in the can. I thought long time ago that it was a little weird that a plethora of ground-based experiments were so slow releasing data. At this point, it becomes almost grotesque, given the costs, as everybody's admitting it. I think community would benefit massively training young people by sharing that data, and I want to reinforce that call. Just people, let it out, okay?
It's not cheap to I could reply to this.
Charles, which argument you are driving an ultimate mission for anisotropy or whatever CMB, BB modes? Which argument would you use to convince people to be recruited to work on and for how many years? Which reward will you promise? You have to set up a crew. Otherwise, as you said, it's too impossible to go on. And you have to convince not only people to work, but the governments to help and to fund the mission. Which argument would you use nowadays with the present governments?
To whom this question is addressed?
Okay, somebody want to reply?
I'll take a crack at it. It's a simple question. It's an important question, but it doesn't have a completely simple answer for this reason. We have examples of missions that have been sold on single concepts. and we have examples of missions that do lots of things. We have examples of everything in between. And I think it's the totality of the science case ultimately that prevails. Now you say, and I would agree with this, that if you write a science case that in total has 150 different things that it will do, then I would quote Gary Neugebauer: design an experiment to do 1,000 things and it will do nothing well. Design an experiment to do one thing well and it will do 1,000 things. That's a focus in the design. It applies to the science case. Don't dissipate the case by just giving one thing after another. Focus on some key things. The Spitzer Space Telescope ultimately was sold on it was designed to do 4 big science areas, and it was limited to that. So the design was only allowed to be affected by those 4 areas. But what it did was huge compared to those 4 areas. Now, if you ask the question again, okay, what's going to be your lead? Well, I think there are a couple of things that need to be in the lead, and I would quote the example of S4 right now. There are 4 requirements. S4 has 4 requirements. The first one is about R. The second one is about neutrinos. The third one is about clusters, and the fourth one is about time delay. Have I got that right, Julian? Ineffective. Ineffective, sorry. Okay, neutrinos, ineffective. Those are 4 pretty different science areas, but they've all been important in making the case. And when you say funding agencies, DOE cares about R, NSF cares about clusters and time domain. So we have to know the audience, have to adopt to that. I think I just demonstrated that the answer is complicated. The question is simple. It's a very good question. It's an important question.
Certainly, I would use the fact of the practical experience of Planck that the legacy value of what was initially targeted for CMB has been have a huge utilization by the community in terms of foregrounds of kind of all kinds of science. So I think we have been not selling well enough the legacy value of the mission, because we drive the requirement with just a few focused things. But in the end, we are delivering maps, well, essentially maps of the sky with an amazing signal to noise and control of systematic. And that's the legacy value, which we should find a way to better explain and the value of. And one thing in practice is just to look at the citation of Planck, and it's just, I mean, it's way above only the parameters.
I'd add just one thing for the space mission, the probe scale. All sky surveys in 20 or 30 bands from 10 gigahertz to a terahertz, exquisite sensitivity, polarization, superb control of systematic errors. That's just an unbelievable richness of data.
Yeah, it's an amazing data set, but is it sellable? That's the question, against having some major science goal, which is not a basket of things, but one single thing.
The way the probe competition the first time was set up, there were 2 modes that were allowed. One was survey, and the other was PI science. In the PI science category, there was a limit of 30% of the observing time devoted to PI science, and 70% had to be devoted to a guest investigator or guest observer program. The kind of thing that we're talking about for the CMB, the scan strategy would be set. You could say where the spacecraft will be pointed any time in the next 5 years. But in terms of using the data set, the uses of the data set are not limited to the things that would be stated at the beginning. And so what those probe missions have done is gone out to the community as Spherex did. Spherex was a great example of doing this, going out to the community and say, what will you do for this data set? Not wait until after you have it, but do it in advance. And the community support then was a major factor. When you think about the flagship missions, this is the case in the US, I know the European situation less well. Flagship missions in the US do not have science requirements, they have capability requirements. And then they have examples of the science that will be done. They'll say, we've designed it to be able to do these things. And then people come in and propose what to do with it. And I think at the scale that we're talking about, $1 billion mission, we're intermediate between the classic for the last 20, 30 years, PI science, more narrow, focused science requirements, and the flagships, which are capabilities. And the capabilities of the kind of mission we're talking about are extreme.
Okay, anyone else from the audience want to have a go? Now's your time, last chance. Okay, very good. So sorry?
Don't you think that CMB is losing its appealing, or the appealing that CMB had 5 or 6 years ago?
I don't think so. But there were two interesting factors that came out in the CMBS4 team in considering the redesign for Chile. One was, how long does it take? And it clearly matters to people and their level of enthusiasm, and young people in particular. How long will I have to wait to do something? Think back to Wilkinson's statement, I don't want to do everything. I want to do something and do it soon. That's one factor. And the second factor is, how big a jump will it be? Big jumps are more appealing than little jumps. And I think put those two together, and we're talking here potentially about really big jumps. And I think that will remain, it certainly remains exciting. After so many years in the CMB, I'm still excited by it. And I think many people still are. So, Armenia, are you still excited by it?
I was told at the end of my PhD that I should start working on galaxy surveys because there was nothing left to do. Yeah, that was like thinking about post-Planck, and I think I've got 20 years of work ahead of me already planned. So yeah, I think we do know as a community that there is a lot more that can be done and that we can do. I think it's trying to understand how can we get there, because I think what you said of do one thing and do it quickly can be in contrast with do a big mission and measure everything. So we need to find the balance there.
Do it as quickly as possible.
Yes. Okay.
So just to say a few words. Well, first of all, thank you very much for all this. You know, I don't have to talk about Lightbird and people talk about Lightbird, so that's great. But just to be very specific, so I'm very comfortable to find that the team will find a solution for detector. But at the same time, I think we might pay the price not by the funding, but by the time. So in the end, this comes back to how soon we want to see the data. And I think delay just drags the community, and that's not good. And just to put in context in very concretely, detector, 5,000 detectors or so, 100 million. That is a number that if you can bring it back, this is the kind of funding we're talking about, to reach to at least, it may not be a comprehensive mission that you might dream of, but this is the very specific mission that we can do, together with all these other outcomes that coming out, including realization and so on and so forth. Whether you feel that this is cheap or expensive, well, maybe you might think this is cheap because you're a cosmologist. Your agency thinks that this is cheap or expensive, that may be different questions. But I think there's a room for contributions, and if you think that there is a room for you to play some role, I think this is now, and hopefully by finding a solution, and this can be again stepstone for the next exploration, like spectral distortion or comprehensive CMB mission, or even gravitational spectrum with the interferometer theory. Hopefully, LightBird make a one stepstone in the cosmology and find the name in one of those books in 100 years from now. So that's all I can say. Thank you.
So thank you, Tomu, for those encouraging words at the end. I'd like us now to thank all the panel members for their interesting contributions. And the final word is coming from Nicola Vittorio via Zoom.